namely whether there is some sort of non-abelian version of Noether theorem. So what do I mean by that? The idea is to obtain a flat connection in place of a closed one form. So the ordinary Noether theorem for two-dimensional variational problems would provide us closed one forms on the worksheet. And what we want, now we have the situation that we have a principal H bundle where H is some Lie group over our target space P mod H. And we would like to now produce, for any map from sigma to the target space, we would like to produce a connection on the bundle which is flat provided that the map is critical. And the idea is to get it from some kind of symmetry. And indeed, it's possible. So there is some reasonably nice answer that we need to extend our Lie algebra H to some Lie algebra G, which is twice the dimension of H, with an invariant inner product such that H sits inside as a Lagrangian Lie subalgebra, or this is the thing which is called the Manin pair, or one can say that H is a Lie quasi-bialgebra, if you wish. And now this G is supposed to act on P. So that's this generalized symmetry would be, or this generalized action. This action of G will not preserve the bundle structure. It will even not map fibers to fibers. It will just slant everything. There is a little bit more to that action that I, for the moment, skip over. One can use fancy words. There is that we're supposed to have some multiplicative gerb over G, which acts on a gerb over P. And also it should be somehow symmetry. It should preserve the Lagrangian density, if you wish, or in case we really have just a sigma model, it means that it should in some sense preserve the metric and the 2 form or closed 3 form, which is on the target space. But in what sense, I'll tell you a little bit later. But let's just accept that such a thing exists. Now I can tell you what is Poisson-Lie T-duality. So first of all, as you can see, it's something quite old, though hopefully I'll tell you also some newer things. And it's going to be isomorphism of two Hamiltonian systems. So what are those two Hamiltonian systems? So let us suppose in the situation that we do have that non-abelian conservation law. That means that we have P over our target space P mod H, and that G actually acts on P. And let us suppose that it acts for group G acts there freely and properly, so that it's actually a principal G bundle. And if now this map F is critical, so we have a flat connection. So in that case, let us simply lift sigma to P horizontally. And then when we choose another Lagrangian subgroup H prime in G, we can project it to P mod H prime. And the thing is going to be, again, a critical map. And okay, this procedure is supposed to be this isomorphism of Hamiltonian spaces. I should give you some more details. So, normally, one is going to suppose that sigma is a cylinder. But in that case, we certainly cannot always lift it, because for that we need to suppose that the holonomy around the cylinder is the identity. So let us suppose that. So that imposes some constraint, which is a finite codimensional coisotropic manifold in the phase space for the sigma model. And it's then the reduction of this thing, which is isomorphic to the reduction of the other thing. So we don't really have a total equivalence of those two sigma. Classically, we don't have equivalence of those two sigma models. It's only for this reduction. Now, how does it compare to the ordinary T-duality or setup? So there, the idea is that all the groups that I talked about so far are just tori. And there, when things are set up properly, this holonomy constraint, that's the requirement that the holonomy is 1, that's simply momentum quantization. So it's not just something random. Now, in Poisson-Lie T-duality, we can either somehow hope that quantization will again provide us with this constraint, or we can simply live with the fact that it's not a perfect symmetry. So let's just take the second possibility for simplicity, say. And, okay, maybe I'll put it back. Now I'll give you some more details, because this was without any details. For the case when P is equal to G, so when P mod G is a point. So here the idea is how to construct it is to construct the sigma model on the boundary of Chern-Simons theory, so much like Bezumin-Witten model is on the boundary of Chern-Simons theory. So here is the Chern-Simons action functional. And the general nonsense now tells us that when this Y is a manifold with boundary, which it's going to be, it's mostly going to be a full cylinder. So then we need to somehow deal with the boundary conditions. And so we would look at the boundary part of the variation of the action. That's what's written there, which is a one form on the space of boundary fields. And we need to make it exact. So we need to choose boundary conditions that will, on which this one form is exact. More precisely, it's supposed to be a Lagrangian, some exact Lagrangian submanifold, something of maximal size. But in our case, we're going to use something very simple. So on that cylinder, on the boundary, we just choose a Lorentz matrix, as once would imagine on a worksheet. And on top of that, we also choose a half-dimensional subspace in G. That's just half-dimensional subspace. There is not a Lie subalgebra or anything. And this R is a reflection with respect to this half-dimensional subspace. And the boundary condition is what's written there, something relatively simple, that on the boundary, the hot star of A is the same as when we apply this reflection on A. And now to give you some of the full details how to get a sigma model with target space H, G mod H. So one needs to also get H into play, because so far it was not there. So to do it completely, we drill a hole to the cylinder. So now it's a hollow cylinder. And we impose the boundary condition. Well, the one that I told you about is more complicated on the outside tube, but simple boundary condition that the connection has values in H on this inner tube. And when we do it, this Chern-Simons action functional is simply a Hamiltonian system. So if you want to know in gory details, which are not written here, so the time component of the connection is a Lagrange multiplier, which forces the space component of the connection to be flat. When we do it, actually, we need to remove some derivative from the time component, so there would be a surface term appearing, which is the Hamiltonian, which is called here H. The phase space where it's happening, so those are flat connections on an annulus. That's when we take a section in for a particular time. So it's a moduli space of flat G connections on an annulus with some conditions. On this inner circle, we're supposed that we're in H, and also that the gauge transformations take place only in H, and inside the gauge transformations are arbitrary, also the connection is arbitrary, and on the outside circle, gauge transformations are trivial. So it's something infinite dimensional. But one can see quite easily there is actually T star of the loop space of G mod H. You can see the loop when you take the holonomy between the inner circle and the outer circle, which is well-defined modulo H. So that's how you get a loop in G mod H, etc. The symplectic form is twisted by some closed tree form, which lives on G mod H. And one can easily see that it's indeed, this is indeed a Hamiltonian description of some sigma model living on G mod H. And as you see now, this H itself enters only very little into the picture. Namely, when we declare that the holonomy of the connection around this inner circle is 1, or we simply remove this inner tube, then H disappears completely, and that's when you get this duality invariant part, that is this reduced phase space, which doesn't contain H anymore, and that gives the proof of the fact that they are indeed equivalent or isomorphic. Now, this construction may be clever, I don't know, but it's not very clear why should we do it this way. And it also works only in case when P is equal to G. So to make have something simpler, the idea is to replace Chern-Simons with a generalization, this AKSZ model. So what is that? Here the idea is simply that you replace your real algebra G with some other symplectic differential graded manifold. Now, here is the axiom functional. Okay, it's written in some maybe fancy way, but once we choose Darboux coordinates on V, then the first term looks kind of the same as for Chern-Simons, only F is a collection of differential forms which are not necessarily just one forms, but forms of different degrees. And there is a second term which is no longer just cubic, but can be a little bit arbitrary. And let me just pass quickly over it. So we can basically do the same stuff as before. So let us take now a solid cylinder. We need to choose some boundary conditions. Again, boundary conditions can be obtained. Sorry, let me try this. So for that, boundary condition of the type that we're going to use are going to be again some reflection in the fibers of some vector bundle which is connected with given by the manifold in this way. So they are just functions of degree 1 are this vector bundle which is called then a Courant algebroid. And as before, we obtain a Hamiltonian system. So this is basically just a little bit more complicated story of what I told you before. That's why I'm not giving you details here. But the idea is that in a particular case, when this V is going to be a cotangent bundle, then things are getting much simpler. So what is that case? So if we take for V somehow the cotangent bundle of T1M, then it turns out that this action function simply is a two-dimensional sigma model on M with target space M. There is nothing happening here. If you want to know the details, then the fields correspond to this T star. They become Lagrange multipliers that basically now interpret all our fields simply as a map going from sigma to M. And there is a little generalization to get somehow closed free form on M. One is to consider twisted cotangent bundle. So for that, we would start with a principal R2 bundle over T1M, then take the symplectic reduction of T star of that. And again, this will give us a sigma model which contains somehow in itself integral of some closed free form. So it looks like WZW model. So if I were to summarize the idea of the talk, the idea is that when we look at just these possibly twisted cotangent bundles, then this AKSZ model with boundary condition is simply the same as a sigma model. So here somehow the idea that WZW is on the boundary of Chern-Simons works perfectly for arbitrary sigma model if we consider this differential graded symplectic manifold. And we can get to other DG symplectic manifold then by reduction or by some Lagrangian correspondences. And these will provide us then those isomorphism or almost isomorphism when we need to impose some constraints of these sigma models of those Hamiltonian systems. So I can now tell you more details about what we actually need for Poisson-Lie T-duality. So as I told you, we start with a principal G bundle. That's for the moment something big. In the end, the target space is going to P mod H, so where H is a subgroup. And this a little bit more that enters to the action of G on P is that we need a principal R2 bundle over T1P, so this is sort of a gerb, which we have over P, if you wish, and which is supposed to be now equivariant, but up to a central extension. So this is what I meant by the fact that we actually have a multiplicative gerb over G, which acts on a gerb which is over P. Or this is a differential graded version of that, which rather than integer version should be in the full story. And the symplectic DG manifolds that are appearing here, so one is going to be simply the twisted cotangent bundle. So we simply descend this XP to over P mod H, so this is what we do. Now we get a principal R2 bundle over our target space. And then we do the symplectic reduction. We obtain just our sigma model, if you wish. Or we can go all the way down to P mod G by taking the symplectic reduction with respect to the entire group, which in the case when P is equal to G just produces back our Lie algebra and would then give us simply this Chern-Simons theory. So the idea is now that the first reduction gives us the sigma model over with target G mod H. The second reduction is gives us the part which is given by this non-abelian momentum constraint and which is independent of H. That means that if you choose some H prime, we get isomorphism of Hamiltonian systems. Okay, so these two Hamiltonian systems are given by the Hamiltonian reduction. Now, where one can go further from here. So one thing, I'll just run over it because there are no results here, that one should look at other dimensions. In principle, there is no problem with considering AKSE model in other dimensions. And following the same strategy. But yes, for some reason, so far, I didn't find anything reasonable here, any higher dimensional non-abelian duality using this kind of setup. And the second thing is, which is mostly open, is quantization. There are some results in this direction, but let me tell you something rather special in this case, that is about discrete, or if you wish, lattice version of this problem. So what is the lattice version of the abelian T-duality? That's what's called Kramers-Vanier duality. That's what is used, say, for determination of critical temperature of Ising model, well, in 2 dimensions. So the idea is that you would take a 3-dimensional oriented compact, etc., manifold Y, and then color its boundary with these 3 colors, some splotches, if you wish. And now imagine that we have a finite abelian group K, and there are K-valued spins sitting in those red splotches, and which interact with each other over those gray things. Here there are 3 things interacting together in such a way that the interaction is K invariant. So then the Boltzmann weight can be written as a function defined on this cohomology group. Now the partition function is then simply this. And this duality says that we obtain the same thing if, now imagine rather K star valued spins sitting in those blue splotches, again interacting through those gray splotches, where the Boltzmann weight is now going to be the Fourier transform of the thing, of the original Boltzmann weight. And the reason why it works, well, you can imagine if whenever you see that sum of something with f is equal to sum of something with f hat, it means that there is a Poisson summation formula going on, which is here combined with Poincare duality to show that this group is the annihilator of the blue group, so to say. And there is just a conjectural picture of what one should do in this Poisson-Lie world when our Poisson-Lie groups are being replaced by Hopf algebras. So the idea is somehow to replace K with a finite dimensional Hopf algebra, and we should obtain a 3-dimensional topological field theory with boundary colored in red and blue, such that the uncolored part of this topological field theory should be just Reshetnikhin-Turayev given by the double of some Hopf algebra. This is our Hopf algebra, which is the space assigned to this square. The product on the Hopf algebra is given by this picture. So we have two H's, and there on the bottom there is one H. And in relation to what I told you before is that when you consider G-valued Chern-Simons on these kind of things, but with boundary conditions given by, well, that on red part is as values in H, and the blue part has values in H star, which is called H prime before, then the quantization of that should be our Hopf algebra H with some of the quantization of the Lie algebra given by this Manin triple. But as I told you, for the moment, this is just a conjecture. And so this is probably neither string nor math, but okay. Thanks a lot for your attention.
Thank you, Pavol. Questions? Yeah.
So you discuss relation between AKZ model and sigma model. So AKZ has a lot of odd stuff, right? Fields, etc. What type of sigma model are you discussing? Supersymmetric, twisted?
No, ordinary. Okay, maybe.
But then I don't follow your statements exactly.
Yes. Because it's incomprehensible. No, the thing is, you see those fields, we have like a map from T1 sigma or T1y going to this space, right? Now, if you consider fields that are given by just those T stars, or somehow those momenta, they are simply Lagrange multipliers, so you can remove them, and they impose some constraint. The constraint that imposes that then the resulting map going from T1y to T1 map to T1m is a DG map, which means that it's simply given by a map going from y to m. I know this y is still three-dimensional, but we don't have anything differential graded anymore. And now what happens that we only get now the boundary contribution to the action. So the boundary contribution is sitting on the boundary, it's integral over the boundary. In the second case, there is also somehow contribution coming from the inside, but that's given simply by its integral of a free form. So it's morally, it's again just a sigma model.
But then you don't need super stuff. I mean, you can just take a current sigma model and run your argument more or less, right?
I'm not sure.
Other questions? Okay, let's thank Pavol again. And I'll resume at 2:30.